Let's review sections 10.2 and 10.4. In your book, pages 529 through 532 and 546 through 550. Remember from the previous video over sections 10.1 and 10.3 that the summary measures for a linear relationship are the slope of the regression line or the correlation coefficient of the scatter plot. In notation, we use rho to represent the true correlation coefficient and beta, the true slope, r, the sample correlation coefficient, and b, the sample slope. If we're doing a hypothesis test for a regression, the null hypothesis in general is that there is no linear relationship between the response and explanatory variables in the population. Note that the null hypothesis, like usual, is about the population, and so we need to use parameter notation. If there's no linear relationship, that would tell us that the true correlation coefficient is 0, or, in notation, rho is equal to 0. If we were testing for slope, no linear relationship would also be indicated by a slope of 0, so beta is equal to 0 would be another way of writing the null hypothesis. The alternative hypothesis is still based on our research question. So rho and beta would stay the same. We still use the same notation. We still use the same value of 0. We just change the sign to greater than, less than, or not equal to, dependent on what we're trying to prove. To conduct this simulation, remember we always assume that the null hypothesis is true, or that there is no association between our variables in this case. If x and y are not related, then we can just break up the xy pairs, shuffle one of the values, and then reassign them to create a new scatter plot. The applet specifically shuffles the y values, but you could shuffle the x's if that's what you wanted to do. Here you see a table displaying the data, where temperature is going to be used to predict the heart rate. So temperature will be our x variable, and heart rate our y, or response. First, we need to explore the data. Here's a scatter plot. How would you describe the form, strength, direction, and whether there are any outliers or not? This appears to be fairly linear, certainly positive, a moderate correlation with no unusual observations. So what would you guess for the correlation coefficient? Something positive certainly, and not very close to 0, but also not very close to 1. The actual correlation coefficient is 0.378, indicating a moderate to weak correlation. So, take a minute and write the null and alternative hypotheses for these data, if the researchers want to know if body temperature is positively associated with heart rates in ICU patients. The null hypothesis here is that there's no linear relationship between heart rate and body temperature in the population. We could write that notationally to either say rho is equal to 0 if we wanted to do a test for correlation coefficient, or slope is equal to 0 if we wanted to do a test for slope. The alternative hypothesis is that there is a positive linear relationship between heart rate and body temperature in the population, or notationally, rho is greater than 0, or beta is greater than 0. Here again is the original data, where we see the body temperature of an individual and then their heart rate within a box. Notice again that the observed correlation coefficient is 0.378. To simulate one sample which assumes the null hypothesis is true, or assumes no linear relationship between body temperature and heart rate, I'm going to take my heart rates, the response, and shuffle them up, and reassign them to a person. So notice that the first person in this data set originally had a heart rate of 72, but that heart rate was moved around and is either now the 97.7 person or the 97.8 person. Because we assume that body temperature is not impacting heart rate, we can say that these heart rates should just be shuffled up and are completely independent of the body temperatures. I get a new correlation coefficient of 0.073. Does that make sense that it is less extreme or closer to zero than our observed? Of course, because we're assuming that the correlation coefficient is in fact zero. So we would expect to get correlation coefficients around zero. If we repeat that process 1,000 times, we would get an output which is similar to this in our applets, where we see a null distribution of shuffled correlations centered around zero, because we're assuming no association, or that the true correlation in the population is zero. We can then find our p-value the same ways as always. We select the sign here of greater than, less than, or beyond based on the research question or based on the sign of the alternative. And then we're going to plug in the observed correlation coefficient of 0.378. Here we would get a p-value of 0.053, or we found that 530 of 10,000 simulations had a simulated correlation coefficient greater than or equal to 0.378, with each simulated correlation coefficient assuming no relationship between body temperature and heart rate. This is providing moderate evidence against the null hypothesis, or moderate evidence that there is a positive association between body temperature and heart rate in our ICU patients. What was just said, with a p-value of 0.053, we don't have strong evidence of a positive linear relationship between body temperature and heart rate for all patients admitted to the ICU, but there is moderate evidence. How could we go about getting stronger evidence? Well, remember, we would want to lower the p-value to get stronger evidence, and one way we've talked about doing that is to increase the sample size. Finally, when would we test for slope and when would we test for correlation? Well, while the slope and correlation are measuring different things and therefore have different values, the signs will always match and will match the direction of the scatter plot. The alternative hypothesis is just about the sign of the slope or the sign of the correlation coefficient. We are just wondering if the slope or correlation coefficient are strictly less than zero, strictly greater than zero, or not equal to zero. Since we're only looking at the sign of the value, the sign of the slope, or the sign of the correlation coefficient, the tests for slope and correlation are equivalent, meaning it wouldn't matter which summary measure you test for, the p-value is going to be approximately the same. So the differences in the test are really these three things. The notation in the hypotheses, we would use beta for slope and rho for correlation coefficient. If we're testing for slope, then we're going to plot the slope from each shuffled data set. And if we're testing correlation coefficient, then we would plot the correlation coefficient from each data set. Finally, the observed statistic, which we would compare to the null distribution, would be the sample slope if we're testing for slope, or the sample correlation coefficient if we're testing for correlation coefficient.